Okay, so to recap what we did on Tuesday, we, including for those of you that weren't here, we have like these sequences of things in R2 and R3, where in R2 we go from functions, which I'm calling C infinity, to vector fields to functions by the gradient map and the curl map. And in R3, we go from C infinity to vector fields to C infinity again via the gradient, curl, and divergence. And we have some general phenomena here, which is that if you compose two of these maps, you're going to get 0. And also, if you go to 0 over here, then you expect to have come from something in the previous step. And we saw that if you fail to satisfy these, then that will detect some sort of a hole. So if you weren't here, then some of the examples that we went over were over here. If you take the magnetic field of like a current carrying wire, then that's sort of something that like moves around counterclockwise, right? And by Maxwell's equations, this has 0 curl. So we expect it to be the gradient of some function, but it can't be, because if you take a loop around the wire, which doesn't exist, or if you take the loop around the wire, then the integral is going to be some non-zero number by Ampere's equation. And so it can't be a conservative vector field for that reason. So the domain of definition is R3 minus the z-axis. And the fact that you can write this as a gradient detects the fact that there's a sort of one-dimensional hole in the space. And similarly over here, you can take an example of an electric field which has 0 divergence, but can't be the curl of something for similar reasons because the Gauss's law was here. But in general, what we saw was that if you do have something, for example, in this R3 case, where the curl of some vector field is equal to 0, then we may not be able to guarantee that g is equal to the gradient of some function, but we can guarantee that it is so after adding on some vector fields which also have curl 0, which sort of represent these holes. So they would be sort of counterclockwise around each of the holes that you have. And for example, like f1, we can modify f1 by like adding the gradient of a function, and it'll still satisfy the same thing, or we can modify it by like scaling by a factor of 2. And it'll still work as sort of something which will fix this problem of not being the gradient of some function. We just have to change our value of lambda accordingly. So what we realize is that this thing detects the number of holes. And this thing we want to ignore. So the definition of cohomology essentially that we're going to come to is, in this case, it's the definition of H1. And this is going to be the kernel of the curl modulo the image of the gradient. So this you should see as the curl is some linear map between vector fields to vector fields or vector fields to functions. And so you're taking the kernel of that, so essentially every vector field which has curl 0. And then you're sort of quotienting out by this gradient part. So you're ignoring anything which comes from a gradient. And what you're left with is these vector fields which detect holes in our space. Does that make sense? Cool. So now we want to generalize this to higher dimensions. And what we have to do is we have to generalize our spaces of functions and vector fields, and we also have to generalize our differential operators. So the most difficult thing to do will be to generalize this one, the curl, and instead of just giving you the definition of differential forms, I kind of want to motivate it from everything that we did on Tuesday. And sort of if we stare at this curl hard enough, it turns out it'll lead us exactly to the full definition of differential forms. So first part of today's lecture is differential forms. Okay, so the problematic thing is this curl differential operator, right? Because in 3 dimensions, this is defined in terms of the cross product. And the cross product is something which only works in 3D. It doesn't work in 4 dimensions or higher. And so we want to fix that and sort of change what we're working with in order to fix that. By the differential forms is going to be the generalization of our spaces. Afterwards, we're going to talk about the generalization of the operators, which is called the exterior derivative. So first off, we want to talk about the cross product. So in math or physics, what do we use the cross product for? Someone give me an answer.
Your vector perpendicular to like 2.
Sure. So you have a vector that's perpendicular to 2 vectors. Can you give me a little bit more than that? It has a little bit more information. what is the length of this vector?
The area of the parallelogram formed.
Yeah, so it's the area of the parallelogram formed by this guy, right? So the crossbar gives you some sort of a measure of the area spanned by two vectors. And the idea is that this vector field is sort of a cheating way to describe that. And what I claim is that this third thing, this first thing is like functions, right? The second thing is like some sort of a vector field, so like some sort of a line element attached to each thing. I claim that the second thing is not functions or vector fields. This actually corresponds to something representing areas. And so in order to convince you a bit more of that, so this is sort of a one-dimensional thing because you only have one function. Sort of a three-dimensional thing because you have three functions, right? But we can unify these two descriptions if we describe both of these as the space of areas in the ambient space that we're working with. So in the plane, we only have like one space of areas to work with, and that's why we only have one thing over here. In R3, we have like a three-dimensional space of areas, and the reason is because like each area has a perpendicular vector. So we have a three-dimensional space of vectors, and correspondingly we have a three-dimensional space of areas that's perpendicular to it. So both of these descriptions are sort of unified if we talk about them as areas. So what we want to do in order to generalize this to higher dimensions is to come up with a good language to talk about areas, and in this case volumes, and so on and so forth in higher dimensions. So our goal here is to come up with a vector space of areas. And so I'll first work in the so-called tangent plane or whatever, but really just like taking a vector space and trying to come up with some vector space that corresponds to the areas of this vector space. So let's start with like some vector space V, which is just R2. So this isn't like R2 where you talk about smooth functions, it's just R2 as like a vector space. And so how can we describe areas in a plane? So one thing that you might think to do is, well, you can make an area by like a parallelogram, right? And so this should be some vectors u and v. So one way to describe this area would be to just keep track of the vectors u and v, right? So I'm going to call such a pair an area element. And the thing is, like, eventually what our goal is to do is to describe something where you have an area and an orientation, similar to how a vector has a direction and a length. And so we're going to want to identify two of these area elements if they describe parallelograms with the same area. So for example, if I have like a unit square, and if I have something of length 2 and length 1/2, these should be identified with the same thing if they lie in the same thing. So what we want to do is figure out some equivalence relation where our space of areas is going to be the set of such ordered pairs modulo some relation which says that when two of these pairs of vectors describe a parallelogram with the same area. So how can we do this? If you go back to literally elementary school, then they teach you how to compute the area of a parallelogram, and they say that if you split the parallelogram into slices, then the parallelogram has the same area as a rectangle because it has the same slices just like shifted over. In other words, what we're doing is we're essentially shearing the rectangle into a parallelogram. So one thing that we should say is that if we shear a parallelogram, then it doesn't change the area at all. So what we want to impose is that u comma v is equivalent to u plus alpha v comma v. Okay, so why is this the relation that we want? Because in this case, I guess let me change the variables. So we'll call this v and this call this u. What we're doing here is we're essentially changing u from this slanted guy to this vertical guy. And what we're doing is we're moving it in a direction parallel to v. Right? So that's what shearing does. It changes one of the vectors in the direction parallel to the other vector. And so we want this to be true, and similarly, we want this to be equivalent to u comma v plus alpha u for any real number alpha. Okay, so what does this allow us to do? This allows us to take any sort of parallelogram, right? And then we can first shear in this direction. And what we'll end up with is this sort of a guy. and then we can shear in this direction. And what we end up with is a rectangle with the same area as our original parallelogram, which is a much simpler thing to do. We just multiply basing, right? But I want a description that's even simpler. I don't know that the formula for the area of a rectangle is base times height. The only formula that I know is that if I have a unit square, then the area is 1, right? So how can we reduce this guy to be a unit square? Well, also in elementary school, they teach you that if you stretch something out by a factor of a, then the area also stretches out by a factor of a. So what we want to impose here is that if you have something like a u comma v, then this is equivalent to what I'll call a times u comma v. So what this means is that you have this area times a. So this represents a times this area. And this should also be equivalent to u comma a b. Okay. Okay. So what have we done? Through the process of shearing and scaling, what we can do is we can take any parallelogram and then reduce it to a rectangle, and then take the rectangle and reduce it to the unit square. And you should check that if this vector is AB and this vector is CD, then by producing, let's call this U and V, then by doing these algebraic operations on this, what you end up with is U comma V is equal to, or I guess in this case, equivalent to E1, E2, which are these two basis vectors, multiplied by the quantity AB minus BC, which is the common determinant formula that you see. And so these two axioms, which I'll call the shearing and scaling axioms, almost determine the area uniquely. You do need a third axiom, which is to say that the area of some special pair, so in this case E1, E2, is equal to 1. So this may not seem like something that you need to impose as an axiom, but the thing is that a vector space does not have a canonical basis, right? So you can choose any sort of any pair of vectors to be your basis vectors, and you can declare that, for example, maybe I say that this shape has area 1, and then this shape wouldn't have the area that it has, but it would have some area relative to this guy. So you have to specify, or in this case, it doesn't have to be E1, E2, but you have to specify some basis parallelogram which has an area of 1. So I guess I'll call this something like the special area axiom. But once you have these three axioms, what you can do with the first two is you can say any parallelogram is any other parallelogram times some constant. And once you specify, in particular, you can bring it down to whatever special parallelogram you chose here, and then you can specify the area of the parallelogram at the end. Does that make sense? Any questions on that? Okay. So now I want to talk about these two axioms for a second. I won't prove this because this was an exercise on the problem session that we didn't go to, but you can do it yourself, is to show that 1 and 2 are equivalent to the following two axioms. Bilinearity, which is to say that alpha u v equal to alpha u v is equal to u alpha v, and also u plus w v is equal to uv plus wv, and similarly uv plus w equal to uv plus uw. So this is, linearity says that you can like pull out scale factors and you can add two vectors either before or after the operation. And this says that you can do so in either entry. And along with this, you also need another property, which is the alternating property, which is that u comma v is equal to negative v comma u. So you can generate an equivalence relation either via these first two and define your space of areas to be that, or you can define it via these two and define your space of areas to be these two modulo this equivalence relation. And they end up being equivalent, and yeah. Who can tell me in R2 what the space of areas is going to be as a vector space? Yeah.
Is it just R?
Yeah, it's just R, because you only have one space of areas, right? We show that you can reduce anything to a single square, and that's all you have. So for a vector space, we need multiplication, which we sort of have by this axiom, but we also need an addition. So how do we add two things? Well, if you have a parallelogram like this, it's not a parallelogram, and a parallelogram, let's say like this, how are you going to add these two things? Well, you want to get a third parallelogram, right? But it's not so obvious how to combine these two in order to get a third one. So what you can do is you can exploit these equivalence axioms and make this guy equivalent to something that's also long and skinny. And then you can just stick these two guys next to each other and then get something that's really long and skinny. So that's how you would add two things here. And so we have defined some space with some addition and some multiplication, and so it becomes a vector space. Yeah, so now let's consider the case of R3. So things get a bit more difficult here. And the point is that you now have things which live in different planes, right? So we can start off with the same definition of taking pairs of vectors up to some equivalence relation, with the equivalence being, again, shearing and scaling. And what happens then is you end up, for example, with your elements being something like a parallelogram in this plane, or you can end up with a parallelogram in this plane, or any sort of plane that you want, right? And these are just described by, again, pairs of vectors, u comma v, or more precisely, equivalence classes of these pairs of vectors. So let's see how what I said carries over. Is there a well-defined scalar multiplication on this set? Yes, how?
Yes.
Oh, it's just the same component-wise thing.
Yeah, so you can just scale any of the one of the vectors by some scale factor. Is there a well-defined addition on this set? How do you define addition?
It's the same shearing thing, you just do it along one of the directions.
Okay, so let me ask you a question. If you have R3, right, you have this one in the XY plane, and you have this one in the YZ plane. What is the sort of common parallelogram that you can make both of them into so that you can stick them together?
You won't be able to stick them flat. You can make one of their sides of the same length in terms of like upper
Sure.
parallelogram, and then like join them that way.
But will that make a parallelogram?
No.
Right. So ultimately what happens is that the same trick that we used for addition, which was kind of ad hoc, no longer works here. And the problem is that if you have two planes which live in different planes, then you can't add them together. So instead what we have to do is, instead of considering this set, what we should really do is just force it to be linear, because at the end we want something that's a vector space, right? So what we'll do is we'll just like take sums of lambda I, ui, vi, and so these are formal linear combinations of these area elements modulo equivalence relation. So now, still if two things lie in the same plane, then by these equivalence relations you can like combine them into a single parallelogram. But this says now that you can add two things in different planes, and well, you can't simplify that, but it'll just like be the sum of two things in different planes. So at the cost of losing a little bit of geometric niceness, we are able to recover the fact that it is a vector space. So I want you to just like keep in mind that this is a little bit awkward, and this is also a little bit awkward, and we'll fix both of them at once in a little bit. But I want to explore this a little bit more. So this one will be represented by the area element E1, E2, and this one by, say, the area element E3, E2, right? So if we take the sum of these two, then a priori they're like linearly independent, right? So it'll just be like the sum of two things. But then the issue is like, if I pick any other plane, I could also pick a parallelogram in that plane, and that would also be linearly independent. If we just like use these two shearing and scaling aspects, because you can't shear one into a different plane, right? Shearing will keep a parallelogram in the same plane that is. So what ends up happening is we have like linearly independent parallelograms in like every single plane, and so we end up with like an infinite dimensional vector space. Does that make sense? So that's the problem, because we want a three-dimensional vector space. So how can we fix that? Instead of choosing these axioms as the equivalence relation, we can instead take these axioms as the equivalence relation. And then what we can do is bilinearity doesn't involve any like shearing process. So we can like use bilinearity over here, and what does that become equal to then? Yeah.
E1 plus E3 on E2.
Yeah. Right. So this is good because now, again, like having lost even more geometry, we have been able to like make it into a three-dimensional vector space like we wanted to. And I'll leave it as an exercise to prove that this is in fact a three-dimensional vector space. But if we draw a picture of this, it might be a bit awkward because what happens is you get like this sort of diagonal parallelogram, right? So let's see if this makes sense in terms of areas. What is the area of this guy if all of the areas of lengths of EI is 1? This is 1. What about this guy? Also 1. What about this one? Is it? So what's the length of E2? Yeah, so this one has an area square root 2, right? So that's also like kind of weird because you're adding two things with area 1, and because they aren't in the same plane, they end up like having an area that's not the sum of the areas. Okay, so how do we fix this problem? Well, this is another thing that's like kind of awkward, and we'll get to this in a minute. One thing I want to talk about before moving on is this notion of an orientation. So I'll just like sort of sprinkle in a little bit as we go, and then it'll become more and more important later on. Because of this property, we can sort of say whether or not two things have the same orientation or the opposite orientation. So what do I mean by orientation? Well, let me first say what I mean for two things that have the same orientation. It would mean that if u comma v is equal to c u prime comma v prime, then if c is greater than 0, we'll say that this has the same orientation. And if c is less than 0, we'll say that has the opposite orientation. So for example, E1, E2 has the same orientation as E1 to E2. And the opposite orientation as E2, E1. Right? So this sort of corresponds to maybe something that you've seen where you take like the order of the vectors that you're looking at, and as we know, like the cross product also sort of takes that into account. So if you flip the order of the vectors that you have, we know that the cross product becomes negative, and that's analogous to this thing. Two things have the same orientation if and only if, so in the plane we can relate any two parallelograms to each other by linear transformation, right? So two things have the same orientation if and only if the determinant of that linear transformation is positive. So in other words, it involves only rotations and scalings and no reflections. So let's look at the same thing in R3. Let's say that we take these two pairs of things in R3. Do these have the same or opposite orientation? Who says same? None. Who says opposite? Okay, most people. Who doesn't know? Okay, cool. So, when I say same orientation, what I mean is they can be related to each other by a rotation and scaling without reflections, right? So maybe it's not so obvious here, but if I make this into E1 negative E2, can someone give me a rotation which will start off here and end over here? So you start off at this square and you want to end off at this one. Yeah, so if you rotate around this axis, right, then you end up from this square to the other square. So, and this one is actually equivalent to the two, you can show that it's equivalent to this guy, which is the two with the vectors flip. And that's in proving that the axioms are equivalent to the alternating property. So in 2 dimensions, these two have the opposite orientation. You can't relate them unless you take a reflection, but in 3 dimensions, you can relate them to a rotation. So what ends up happening is orientation of areas does not make sense in 3 dimensions, but an orientation of a volume would make sense. The point is that you don't have an extra degree of freedom to like sort of rotate around. And this makes sense because, like, for example, in 2 dimensions even, it doesn't make sense to say that 2 vectors have the same or opposite orientation because you always rotate one to the other one. But in 1 dimension, say, you can say whether or not 2 vectors point in the same direction or opposite direction because you can't get to them without reflecting. So that's just a little bit on orientations. And now let's talk about 3-dimensional stuff. So how do you describe volumes? So to describe a volume, we're going to do a similar thing. Instead of taking pairs of vectors, we're going to take triples of vectors. So let's change this to triples of vectors like that. And let's still take formal linear combinations because if you take volumes in 4 dimensions, for example, then you're going to run into the same issues. And then we're going to take this modulo the same equivalence relation. And here you still have like the same 2 axioms. So you still have a shearing property and you still have a scaling property. So scaling property is straightforward again. If you stretch one of them, then the volume will stretch likewise. And shearing property, sort of like to think of like you're poking gel or something and then just like ripples back and forth. It doesn't change the volume at all. So it's the same thing, except what you can do now is, I'll show you an example. So UVW is equivalent to AUVW. And over here, what you can do is you can shear by any direction in the plane of the other 2 vectors, right? So you can add some constant of V, and you can add another constant of W, and this should be equivalent. And likewise for the other 2 things. And these axioms, which again are more geometric, are equivalent to other axioms over here, which are multilinearity, which essentially says that, I want to rewrite it. It's like linear in each argument, right? You can pull out scale factors in each argument, and you can split off sums in each argument. And the alternating property. So this one's a bit more interesting. So this one says that UVW is equal to minus VUW. And if we swap these 2, for example, then this will be the same as VWU. So each time you swap 1 pair of vectors, it gives you a negative sign. But if you swap 2 pairs of vectors, then it gives you 2 negative signs versus a positive sign. And this is a reflection of the fact that in 3 dimensions, if you take 2 reflections, you can actually make that into a rotation by 180 degrees. Okay, so in general, what's the sign going to be? Does anyone know what the sign is going to be if you take like an arbitrary permutation of the elements? Yeah.
It's like how many times you swap it, like whether it's even or odd.
So it's how many what's called transpositions, which is how many times you swap a pair of things. And this has a name. It's called the sign of the permutation. Very creative. And so the way that I like to think of it is like, these are the more geometric axioms, which make more sense. This is saying that these are the axioms which you have in order for two things to have the same volume or area or whatever. And these are the more algebraic axioms, which is what we're gonna go forward with. And this is usually what they start off with in textbooks, without explaining why you would want these axioms at all. Yeah, so let me say that if you do the same thing with like k-dimensional spaces, then you end up with k-equal pairs of vectors, modulo some equivalence, and that will represent the space of k volumes inside your n-gain space. So if you have your vector space V is equal to Rn, then the space of k volumes inside Rn is notated by lambda k V. And this is the thing that we've been doing, which is like formal linear combinations of these guys modulo the equivalence relation. Yeah.
Wait, I'm sorry. So what's your argument for why this is natural for, like, for instance, areas in 3 dimensions? Like, is there a geometric way of seeing it?
Seeing what?
Why you should be using those axioms as opposed to?
Well, these, remember, like, if we were like adding two planes in different planes, then they were linearly independent if we use these axioms. So since we want to end up with like a 3-dimensional vector space in that case, what we want to do is still be able to combine these two in some way, and so we'll actually use these guys. And like this is again a bit awkward and not great, so we're gonna fix that like right now. But yeah, these are the more algebraic axioms which work. But those are like the geometric axioms which I think you should like keep in mind as to why these are the axioms. Yeah.
So you said that in 2 dimensions for areas, the geometric axioms, the first two, are equivalent to the algebraic ones.
Yep.
But in 3 dimensions, they're not equivalent.
For
the
areas.
algebraic ones are stronger.
Yeah.
Is there like an easy way to see why the equivalence like breaks down?
The thing about the two planes.
I guess like algebraically, why does quotienting out by that like not give you enough equivalence?
I think it's because of the subtlety and like the way that we defined addition.
Okay.
Because you could always combine any two parallelograms in the plane to define addition over there.
Yeah.
So that means that addition over here was the same as formal addition of parallelograms, but over here we're using just like formal addition regardless. So this addition is formal addition, whereas that addition is sort of like, there's no formal addition over here. Right?
Oh, so there you're also quotienting out by some addition thing that isn't in the formal vector space. It's like extra. Like,
what do you mean?
Like there you're quotienting out by a relation that has addition in it. Like u plus w comma b is u b plus wb. And that relationship is stronger than the geometric thing.
Yeah, so the point is like this has a sum like on the outside, right?
Yeah.
Yeah, this, here you don't have any sums on the outside.
Right, so the only addition in that case is the formal addition.
Yeah.
Yeah.
So in this case it's the formal addition.
Yeah.
Over there was the sort of ad hoc thing that we
Yeah.
defined. Yeah. Yeah, that's a good question. Okay, so how can we remedy the fact that this is kind of awkward, that we're taking a formal linear combination of area things and like this weird stuff of like formal addition and like combining things which aren't the same thing? So the point is that like we haven't like touched upon this guy at all, right? So what we've done is we have described when two guys have the same volume, but we haven't actually said what that volume is. So in R3, for example, what you would like to do is to say, okay, in this plane, I'm gonna choose a canonical area element. This area has area 1. In this plane, I'm gonna choose a different one. This thing has area 1. And this guy, I'm gonna choose a different thing. This guy is area 1. But then you can choose like some other plane and also choose an independent area that also has area 1. And again, you run into this thing where you can like specify arbitrarily many areas. But that gets into an issue of that gets to an issue again of like you have like an uncountable many specifications where we only want a 3-dimensional vector space. So instead what we can do is we can sort of linearize this and we can say, okay, let me define some function omega, which goes from lambda kv to r, such that this is linear. So omega of, I don't know how to write this, a1 plus a2 is equal to omega of a1 plus omega of a2. So if you're looking at two things which lie in the same plane, then this makes sense, because all you're saying is if you take the sum of the two parallelograms, then the resulting thing should have the sum of the areas. But if you're taking two things in different planes, then this is saying something new. This is saying that if I know the area in this plane, I know the area in this plane, then that'll also give me the area of like the formal linear combination of these, which by linearity we saw as this diagonal sort of a plane. So if we know these two areas, we'll also know this area. And so what that means is that we only have three linearly independent areas that we can specify. And after we specified those, we have determined the area in like every single plane. Does this make sense? What this does is, it sort of fixes all of our problems that we have. This formal linear combinations now, we don't have to look at this anymore. What we can instead do is like define omega as being a function from k copies of v. And, or I don't know if I should say that. You can define some sort of basis area things, right? So let's say that I'm gonna just like come up with a name. So epsilon1, epsilon2 is something that if you plug in E1 and E2 as vectors, so this is gonna take in two vectors and give you some area. And so what this guy is going to be defined as is this will eat in these two vectors and give you an area of 1. But if you feed in anything that isn't in the plane, so like this guy, then it'll give you 0. And likewise, you can do the same for like epsilon1, epsilon3, epsilon2, epsilon3, and so on. And so I'm not explaining what this is right now. I'll explain in a moment. But just think of this as like this is sort of an area specifying an area in some plane. Which I'm using this epsilon1, epsilon2 to sort of indicate that this is like the dual to E1 and this is dual to E2. And once you do this, you can define your omegas as sort of being linear combinations of these guys. So you can say, for example, take omega equals 2, epsilon1 wedge epsilon2, plus 3, epsilon2 wedge epsilon3. And so what this is doing is like, this is some function which takes in two vectors and gives you a number. And this is some function which takes in two vectors and gives you a number. And so all you're doing is you're like adding functions now. And this makes more sense than like adding formal linear combinations of areas. What you're doing is just adding functions. And we'll see that this becomes something which looks like dx dy plus dy dz. And this hopefully shouldn't be as scary, because if you see this under integral sign, you should, in theory, know how to deal with that. So that fixes that problem. And it also fixes this problem, as we said, of determining what the area is. And so the space of all such omega is equal to, by this, the dual of this guy. Has anyone not seen dual vector spaces before? Okay, a dual vector space is the homomorphisms from lambda kv to R. So just linear maps from your vector space to R, and so you can think of these as like row vectors, for example. And what you can do is you can actually describe this itself as sort of, by the way, this guy lambda k is called an exterior algebra. Or a wedge part in this case, actually. So you can describe this set itself as a wedge product as being lambda k of v dual. And so what I mean by that is I'm now going to explain what this guy means. So what you do is you start off with v dual, which is homomorphisms from V to R. And again, you can think of these as row vectors. So to every basis vector, you have a dual vector. So for example, epsilon1, or let me just write the full thing. Epsilon I of ej is equal to delta ij, which means that it's 1 when I is equal to j and 0 otherwise. So these are just like epsilon 1 detects E1, epsilon 2 detects E2, and epsilon 3 detects E3. So once you have these, then you can sort of specify what areas should be. So in 2 dimensions, for example, if you take epsilon 1, there's going to be some notation that I'm going to use. And if you evaluate this on the vectors AB, CD, then this should be the thing that gives you the area of these two in the plane. And we saw that that is equal to AD minus BC. And how can you write AD and BC in terms of these epsilons? Well, we can write this as epsilon 1 E1, epsilon 2 E2 minus epsilon 2 E1, epsilon 1 Does that make sense? Similarly, we can extend this definition into 3 dimensions, where let's say that we take ABE and CDF, and this will give us still AD minus BC, and this guy. Yeah, you had a question?
Should E1 and E2 there be like the vectors A, B, and C, D, not the basis vectors, but E1, E2?
Yes. So I'll propose to you. Yes. Thank you. So this epsilon 1 of U gets out the x component, and epsilon 2 of V gets out this component, and so on and so forth. And so what this does is it's sort of, the geometric interpretation of this is you are projecting down onto the plane first. So you're replacing this E and F by zeros, and then you're computing the areas after projecting down onto the plane. And something which I'll mention, but I won't dwell on too much, is that the epsilon i's as a whole depend on the ei's as a whole. So if you change just what E3 is, it turns out that also changes epsilon 1 and epsilon 2. And the geometric reason for this is I said that this corresponds to like projecting down into the plane, right? So let's say that you take this diagonal area that we were looking at. So how can we project this down into the plane? Well, you'd probably say it's projected down and then you get the unit squared, right? But what if I instead projected down along the diagonal? Then I would just get like a straight line, and that would have an area of 0, right? So what happens then is the direction along which you're projecting depends on the other basis vectors that you choose. In this case, in the first case, we were just projecting down along E3. In the second case, we're projecting down along E1 plus E3. So that's sort of the dependence on the dual vectors on your original basis vectors. So in general, you have this sort of a formula, which is like epsilon 1 up to epsilon k, acting on U1 to UK. And this is essentially, okay, I'll write the formula and I'll explain it. So this is epsilon 1, U1, epsilon 2, U2, epsilon k, UK. And then plus, for example, like epsilon 1, you can swap the first two. And in this case, it'll pick up a minus sign. So what's going to happen is you can sort of permute these u's inside and act each epsilon on some u such that every u gets accounted for exactly once. And then you put a plus or minus up front depending on, again, the sign of the permutation that you use on these guys. And so you'll have a bunch of other things over here. And essentially what this models is the determinant formula. This is a sort of generalization of the determinant formula because I never said that this was inside a k-dimensional space. This can be in any sort of n-dimensional space. these vectors, and you just like act on them by sort of picking out each one of them by some permutation. Does that make sense? I feel like I went through that a bit fast. Yeah.
When you change like EI, that changes every epsilon j besides the j of the I, right?
I believe so, yes. Yeah, basically, epsilon I, what it's doing is it's projecting away from the rest of the basis vectors.
Right. Yeah.
So, what happens is, for example, in 3 dimensions, let's say that you pick some basis. Each pair of basis vectors determines a plane, and the third epsilon projects all this plane into a single point.
So the third epsilon doesn't care about what E3 is, it only cares about E1, E2.
And so if you've seen the formula that like the dual vectors will be acted on by the inverse transpose of the matrix, you can show that. Yeah. Cool. So this is the object that we care about. Anyone have any questions on this before we move on? I will say to relate it back to here, what we're gonna actually take is the space omega k of, I'll just write M for now. For now you can think of M as some subset of Rn. And what this is gonna do is it's gonna attach one of these guys to each point in your space. And the way that we write that is something, for example, like dx1 dx2 plus 3 dx2 dx3. And so what this does is, so you have a 3-dimensional space, you look at this point, and you say, okay, this is these are called forms, K forms. This is a 2 form because it has 2 of these guys. And so you have 3 directions, which is the first direction, second direction, and third direction. And what this is saying is that this is the epsilon 1, epsilon 2 that we were dealing with earlier, but restricted to sort of tangent vectors to this point. Okay? And what happens is you can like sort of have something which has a function over here. For example, you have something which looks like x1 over there. And so what that's doing is, if you look at a point, first evaluate the coefficients at this point, and then use those as the coefficients for the area elements. So for example, if you're looking at the point 0, 0, 0, then this would become dx1, dx2, and it's computing the area inside, let's say like this is 1 minus x1, okay? So it's gonna be computing the area inside the x1, x2 plane. But then at the point 1, 0, 0, this is gonna be dx2, dx3, so it's gonna be computing the area in the yz plane. Does that make sense? Yeah.
Do your like e's and epsilons depend on the value of x, or are they fixed over all space?
For now, they're fixed. Yeah. We'll see later when I talk about manifolds how to do it in general. But for now, they're fixed. So what is this guy? Why is it useful? Well, as you may imagine, it's useful because you can integrate them, because it looks like the things that you integrate. So let me talk a little bit about how you integrate things. So a K form you can integrate over a K-dimensional submanifold. And the way you do that is as follows. So let's say that we work with this 2 form in R3. And we want to integrate this along this surface sigma. Okay? So integral over sigma, and usually the name for these guys is omega. So I'm going to call this omega. How do we do this? Or, okay, not computationally how do we do this? I'll give you a problem on that later. But sort of, what's the idea of like what's going on in the background? So how you can describe sigma is a map from the plane into our space, right? This is essentially saying that you have 2 coordinates, theta 1 and theta 2, and you map it into our space. via some f1 of theta and f2 of theta, right? So the idea now is that this true form takes in two vectors at every point and gives you a sense of the area at that point spanned by those two vectors. Yep.
Wait, why is the mapping only two-dimensional instead of three-dimensional?
Because I forgot how to do math. Yeah, so omega is gonna, at any point, take in two vectors and give you the area spanned by those two vectors. And so what we're doing is we're sort of taking a non-linear version of like the sum of areas. And the reason I say it's non-linear because instead of just like taking the area of a parallelogram, we can take the area of any sort of surface. And the way we do that is we decompose the surface into little pieces, compute the areas of each of those little pieces according to this omega, and then add those all up together. Right? So what we can do is we can discretize this guy, and then that'll end up discretizing our surface. And at each point inside the discretization, what we do is we say, okay, let's take two vectors, which are the vectors, so this vector is gonna be, if we increase theta 1 by a little bit, then that's gonna move in this direction, for example. And if we increase theta 2 by a little bit, that may move in this direction, right? So we can take the two tangent vectors, which is the derivative with respect to theta 1 and the derivative with respect to theta 2, feed them into omega, and that'll give us some number. And then we take the sum of those numbers over all the points, and that'll give us our integral. So if I write this as f, then what this is doing is it's taking the sum over some mesh of omega of the derivative with respect to theta 1 of f, and the derivative with respect to theta 2 of f. Does that make sense? Any questions about how integrals work? And sorry, this should be like times some little dA, where dA is like the area, dA sub theta, where dA sub theta is the area of theta over here. So I'll give you an example problem where you like compute the area of a sphere next week, and then you'll sort of hopefully see how to actually compute these. But does the idea make sense here? Yeah.
Are we choosing theta 1 and theta 2 as any arbitrary vectors?
So can someone tell me why it doesn't matter what coordinates we use? Yeah.
They get like a factor of the Jacobian interchange.
Yeah, so you can really nicely interpret the Jacobian in this case. When we talk about manifolds, I'll talk about pullbacks a little bit, and Jacobians will make sense more there. But essentially, Jacobian will say the amount that we've like sort of changed the coordinates by, that like sort of squeeze this area by some amount, right? And Jacobian stretches the area over here by the same factor so that they end up canceling out. And then you end up with the same integral. Basically, change of coordinates formula in multivariable calculus. Any questions on this? Okay. In that case, let's move on to the second topic, which is the exterior derivative. Okay, so I mean, just to sort of remind you where we're going, we define these spaces, which is the generalization of C infinity functions in vector fields. Actually, let's see. What is omega 0 of M? What is omega 0 of R3? So it's R at every point, right? So this is like, when I write lambda, I mean like R3 as a vector space. When I write omega, I mean R3 as a manifold. So you're like taking one form at every point.
Oh, is it C infinity?
Yeah, so this is the space of functions, right? What about omega 1 of R3?
Have we defined what omega is?
Yeah, I said it in words. Okay. Let me sort of copy of lambda k of Let me just find for Rn for now. Rn at every point. So this is saying that I'm going to tell you what k-dimensional areas are at every point, but k-dimensional areas in the sense that you take tangent vectors at each point, which is like tiny vectors, vector field sort of stuff. Does that make sense? Okay, so what should omega 1 of R3 be?
Like vector fields with 3 components.
Yeah.
Under bar 3.
So technically speaking, it should be like the dual space of vector fields because vector field should be a vector at every point, but this is something which eats in a vector and gives you a number. So the way you should think about this is that at every point it eats in k vectors and gives you a number. There's sort of a generalization of area at that. What should omega 2 of R3 be? Guys, in this case, we'll just say up to isomorphism.
Same thing.
Yeah, so up to isomorphism is also vector fields because again, we have like a 3-dimensional vector space at every point. And then omega 3 of R3 should be what?
Same thing.
Yeah. And why is that?
Because there's only like one choice of like 3.
Yeah, so similar to how there's like one area in 2 dimensions, there's only going to be one volume in 3 dimensions. And so you have one volume element at every point. In other words, you have a copy of R at every point. And so you end up with this guy. So you can see that that exactly gets us to where we wanted.
Where did like the continuity come in from? Because like, are these like copies related to each other somehow then?
Yeah, I'll say that they're copies which can be written in the form, the sum, okay, so I'll introduce some notation. Sum of fi dxi, here I is a multi-index. So multi-index is some subset of 1 through n, and the size of I is the size of the subset. So for example, dx sub 2, 3 is by definition dx2, dx3. And I should also say that people are sloppy. What they mean by this is dx2 wedge dx3. And so what that means is this is actually equal to negative dx3 dx2. So it doesn't matter what order you put things in.
And now all the f have to be smooth.
Yeah, and all the f have to be smooth.
Thank you.
Other questions? You can sort of relax smoothness sometimes if you care. In more serious cases, like sometimes you take f to be complex valued and you take them to be like holomorphic or something. Maybe we'll talk about if we have time at the end. But yeah, in this case, it's just like that the smoothness of f is what guarantees smoothness of these guys.
Yeah.
Okay. Can someone give me the actual time because the clock is off? It's 8:10. Okay, we have 20 minutes. We can start talking about this. Yep. Okay. 2. Exterior. Can someone tell me when it's like 25, and then I'll know when to stop soon after. Okay, so we've generalized the spaces that we wanted. Now we need to generalize the linear maps that we want, right? So we're going to define some operator, dk, which goes from omega k to omega k plus 1. And eventually, I'll stop writing the k's for the d, and I'll just call it d. But for now, we'll keep it in there. And what should this operator be defined as? So the definition is as follows. Let's say omega is equal to the sum of fi dxi. By the way, was there any question on this notation? Does this make sense? Okay. This is just some indexing for the function. So to every I, there is some function. Such that size of I equal to k. And then definition is d omega is equal to the sum over I times the sum from I is equal to 1 to n of partial I partial xn dxn dxi. where again, this is like taking the wedge of these two. And then you have a theorem which goes along with this, which is nice. It's called Stoke's theorem, which says that the integral over omega of d omega is equal to the integral over the boundary of omega. Okay, so as I said, differential forms are really just things that you can integrate. That's sort of what they're used for. And yep.
Are those n supposed to be lowercase I? Like the index for the inner summation? Or
Yeah. Thank you. So
also the derivative from the x.
So this is a thing. And why do we want this to be true? Well, remember how like on Tuesday we were using a lot of like fundamental theorem of calculus, Stoke's theorem, divergence theorem. Well, they're all like the same thing really. So if you look at the fundamental theorem of calculus, right, it says that the integral from a to b of the gradient of f is equal to f of b minus f of a, right? And then what does Stoke's theorem say? It says that the integral over some surface of the curl of some vector field equal to the integral over the boundary of the surface of the vector field itself. And the divergence theorem says that the integral over some volume, the divergence of some vector field is equal to the integral over the boundary of the volume of the vector field itself. So I'm going to draw some suggestive pictures. So what if we take the special case of like a cylinder? And what if we take like special case of like you have like two spheres at the end and you sort of like fill in this tube in between them. So you can see that these are all like kind of saying the same exact thing, because in this case the boundary is just going to be like these two circles. We take this guy minus this guy. In this case the boundary is going to be these two spheres. We take this guy minus this guy. Except these statements are a bit stronger. They're sort of a stronger generalization of the fundamental theorem of calculus, because you can also like do some more interesting figures like this, which if you don't know is called a pair of pants. So yeah, and also like in this case you can also do some sort of more interesting things, because if you take like multiple curves at once, then you can sort of consider the union of these curves to be some c. And then what this is doing is taking the integral over the boundary of c of f. Where what I mean by this is just like each of these has an orientation. So just take the endpoint, evaluate at f, and subtract it from the initial point. So this integral becomes a finite sum. So all these are really saying the same thing, and that generalizes into Stoke's theorem. Okay, so this is how it's usually presented. They give you this definition, and then they prove Stoke's theorem. When I first read the Stoke's theorem, I was really excited. In Bottom 2, which is one of the references I gave, it's like 2 paragraphs. I was disappointed that the theorem was so short. Every single person I've talked to has said the proof of Stoke's theorem is really disappointing, because once you set up the machinery of the exterior derivative, it's almost immediate. So instead what I'm going to do is I'm going to take this as the definition, and take this as the theorem. So we're going to figure out why this should be the definition of the exterior derivative, given that we want this to hold. And hopefully this should be motivated enough, because we use this a whole lot on Tuesday. Does that make sense? Cool. So this is a long and tedious computation, which I have written out because I knew that I would mess it up. Okay, so how are we gonna figure out the formula for this? Let's do the following. I'm gonna consider the case where we're working in R2, and we're looking at D1, which goes from omega 1 to omega 2. And what we're going to do is we're going to take a really small square. And this is the point xy. Okay? And this vector is some little length ex, and this vector is some little length dy. So I'm going to sort of do this physicist style, and like from this work in a really tiny space, and then derive this formula, which may seem a bit sketchy, but then this is like, I think the only way that you can ever arrive at this formula if you didn't know it beforehand. And then you can check that it does the thing that you want it to do. Okay. So how are we gonna do this? We know that omega is a one form in R2. So this is gonna be written as some omega x dx plus omega y dy. And we also know that d omega is supposed to be some two form. It's supposed to be something that you can integrate over the surface, right? So this is going to be equal to some omega xy dx dy. Okay, so we know this. We want to figure out this. So how can we do that? Let's just evaluate it on some really tiny square and figure out what happens. So we have that d omega evaluated on these two vectors. So yeah, the integral over this guy of d omega is just going to be omega evaluated at this point, right? I'm going to use subscripts to denote what point is being evaluated at, because we're going to need that in a bit. So this is the integral of d omega over this square. It's just going to be equal to d omega evaluated at this bottom point evaluated on these two vectors. Cool. And this is going to be equal to the integral of omega over the boundary of this guy, which means we traverse the boundary and we figure out evaluate omega on each one. It's going to be omega, and this is where we have to be careful. So what I'm going to do is I'm going to sample omega at the midpoint. For convenience, you can not do the midpoints and be more careful if you want to. And then evaluate on each of these four sides. So this first side is going to be omega xy, evaluated on the vector delta x dx. The second one is going to be up this way. We have to take counterclockwise orientation, by the way, which should make sense from Stoke's theorem. And this will be omega, sorry, I said I was going to take midpoints. X plus delta x over 2 comma y. So over here we're looking at this point, which is x plus delta x, y plus delta y over 2, evaluated on delta y ey. And then omega, we're looking at this top point now, x plus delta x over 2, y plus delta y, and then delta x dx, and then omega sub x y plus delta y over 2, delta y dy. Okay. Who can tell me why this formula is wrong? And there may be more than one reason depending on if I actually made a typo from what I intended. So we're like traversing the square counterclockwise, and we're evaluating each vector at each of these midpoints. Are all of the, so the points are correct, I'll tell you that. The vectors are wrong, some of the vectors are wrong. Why?
Shouldn't some of them be like divided by 2? Or like combinations of?
For what?
Cause like when you're going from like one edge to the other, don't you need like?
So here we're going from here to here, and then we're going from here to here, and going from here to here, and going from here to here. So this one is just in the x direction, this one's just in the y direction, this one's just in the x direction, this one's just in the y direction.
Oh, so it is
Signs.
negative.
Yes,
Yeah.
which ones need to be negative?
The bottom.
Yeah. Right? Okay, so what is this thing up top? I said that d omega had this form, and we're feeding in ex and ey, and x dx dy on ex ey gives you 1. And then by linearity, you can pull out the delta x and delta y. So this is going to be equal to delta x, delta y, omega xy, which is what we're trying to figure out, x comma y. Make sense? And then these guys, well, this only cares about omega x because if you're only evaluating on the x direction. So this will be omega x. Actually, let me just do this. So this only cares about omega x, and then multiplied by delta x by linearity. This is omega y multiplied by delta y by linearity. This one's also omega x multiplied by negative delta x by linearity. So I just put the negative sign in front. And this one is negative delta y omega y. Okay. Can someone suggest to me what the next step should be? What things seem similar? What can you do with them? Yeah.
Like you group the delta x and delta y terms together, and that looks like a difference of omega x at like nearby points.
Mhm.
So you can write it like as a derivative, like mean value theorem.
I should put it in a box. Okay. So here we have a delta x plus the other term. Here we have a delta x times some difference. And what we want is delta x delta y times something, right? So what we can do is we can do our favorite trick and multiply by 1. Right? And so in the limit as delta y goes to 0, what does this thing look like?
The y derivative of omega x evaluated at x plus delta over 2, y
Close.
plus delta.
It's not the y derivative, it's something times the y derivative. Which one has the plus delta y?
Oh, the one further out. So
Okay.
it should be negative times y.
Yeah, because you're taking negative times the 1 plus delta y, so you get negative delta x delta y times the partial derivative of omega x with respect to y. Okay? And here, what you end up with is a similar thing, delta y times omega y of x plus delta x, whatever, minus omega y x, whatever. And similarly here, you can multiply by delta x, divide by delta x, and what you get is the derivative. And so what you get is plus delta x delta y times the partial derivative of omega y with respect to x. Does that make sense? Yeah.
Do we want to specify where we're taking the partial derivatives?
Yeah, technically, but I don't care anymore.
Oh.
So the point is that the reason I put these subscripts is because if you didn't put the subscripts and you pretend that you're validating everything at x, y, then this would just be 0, right?
Yeah.
But because you're evaluating at y and y plus delta y, then you can take a derivative. Now the thing is, if you do keep track of the point, the difference from like x plus delta x over 2 and evaluating it at x is going to have a factor of delta x, right?
Yeah.
Here we also have a factor of delta x. So what that means is that you're going to have a factor of delta x squared. So whatever the difference is in like where you evaluate the point is going to be vanishingly small. So you don't actually care. Yeah, so if you want, you can try formalizing that, but that's the idea. So in effect, what you can do is you can just evaluate this at x, y at this point. And anything else you can check as something like delta x squared or delta y squared. And as you take delta x small enough, like these guys get like vanishingly small, so they don't contribute. And so now, since we have delta x delta y times something, delta x delta y times something, what we conclude is that omega xy is equal to negative derivative of omega x by y plus derivative of omega y by x. Or stated more clearly, d omega is equal to negative del omega x del y plus del omega y del x dx dy. And here what you have is like these two almost look the same, except this one has a negative sign. So what if we flip the negative sign by flipping these two, right? So this is equal to omega x partial y dy dx plus omega y partial x dx dy. And yep,
I just wanted to let you know that it's 26 because you asked.
thank you. I'll finish up soon. So you can see that this formula agrees with this formula. And the reason that you have like dxi going first is because in general you're gonna have like a plus or minus sign, and this determines the sign. And if you're curious as to what the sign represents, actually first let's do this. Let's go from omega 2 to omega 3 in 3 dimensions. And what you can imagine is you're doing like much the same thing, except here you're taking a cube, right? And so what's gonna happen is you're gonna go around the surface of the cube, right? On the left side, you're gonna have something involving the volume, which is just evaluating on the 3 vectors independently. And on the other side, you're gonna have each of the faces of the cube. And so what's gonna happen is you're gonna, for example, look at the top and bottom face of the cube, and then take the derivative of that, because you have the difference of 2 terms, take the derivative of that with respect to z. And then you're gonna take these 2 faces, take the derivative of that with respect to x, these 2 faces take the derivative of that with respect to y, and then you get a similar thing over here. This is like the face that you're evaluating on, and this is like the direction perpendicular to the face that you take the derivative with respect to. And the only other case that I want to talk about is the same thing omega 1 to omega 2, but in R3. So in this case, you have you have 3 possible squares that you can check, right? You have the xy squared, you have the yz squared, you have the xz squared. But each of these is linearly independent, so you can just do the same computation and you get this sort of a thing, and then it reduces to this formula. And if you're wondering as to what the signs are, what ends up happening is you have some sort of an orientation on your square, and the sign is such that like this direction goes up, right? So the sign over here is going to be such that if you take the outward facing normal, it should have the same orientation as this guy. So if you take the outward facing normal over here, these 2 vectors have the opposite orientation, which is why the top side over here had a negative sign. So that's sort of how the signs come about. And that's the definition of the exterior derivative. Next time, I guess we'll verify that the exterior derivative recovers all this curl gradient divergence stuff. And then we'll define cohomology. I can actually define cohomology right now since we've already done that, but I'll explain why cohomology works the way you want it to next week. And so this is the kernel of dk modulo the image of dk minus 1, the same way we had for here. Any questions on the derivation of the exterior derivative? Why we care about the exterior derivative? Anything like that? If not, I guess that is all for today. And then I'll see you guys on Tuesday, which will be another lecture, and then the following session will be on Thursday.